Good day, everyone. For today's topic, we will talk about second-order equations reducible to first order. I am Earl Tomac, and together with my co-presenters, Ms. Mingito, Ms. Kailing, and Ms. Coquilla, we will help you learn more in solving this type of equations. But first, you may want to have a sheet of paper with you to take down some notes. So how are we going to solve second-order equations reducible to first order? Now, this type of equations are usually in the form of p of x, y double prime plus q of x, y prime plus r of x times y equals g of x, where p of x, q of x, and r of x are continuous functions. When we have g of x equals 0, it is a homogeneous linear equations. And when we have g of x is equals to some other numbers or not equal to 0, it is a non-homogeneous equation. Now, when p, q, and r are constant function, we have this equation ay double prime plus by prime plus cy. The typical solution for this equation is y is equals to e raised to the power of rx, and we have to take the first derivative. So we have r times e raised to the power of rx, and again we have to take the second derivative. We have r squared times e raised to the power of rx, and substitute the values of y prime, and y double prime to the equation. So we have a times r squared times e raised to the power of rx plus b times r times e raised to the power of rx plus c times e raised to the power of rx equals 0. So by factoring this equation, we have e raised to the power of rx times ar squared plus br plus c equals 0. Now we have to divide both sides by e raised to the power of rx. So we have ar squared plus br plus c equals 0. Now in solving for the value of r, we have two ways on finding its roots or its value. So we have the factoring, and the other one is by using the quadratic formula, r equals negative b plus minus square root of b squared minus 4ac all over 2a. Now, in finding the value of r, we have three cases. So for case 1, when the discriminant b squared minus 4ac is greater than 0, so we will have two unequal roots. And for this example, we have r equals 3 and r equals negative 3. The general solution for this would be y is equals to c sub 1 times e raised to the power of r sub 1 or the first root times x plus c sub 2 times e raised to the power of r sub 2 or the second root times x. Now for the second case, we have when the discriminant b squared minus 4ac is equals to 0, we have only one root. And the general solution for this would be y equals c sub 1 times e raised to the power of rx plus c sub 2 times e raised to the power of r times x, where r here is our one root. For the third case, we have when the discriminant b minus 4ac is less than 0, then we will have the roots as imaginary numbers and complex numbers. So for example, the first root or r sub 1 would be alpha plus beta times I. And the second root or the r sub 2 would be alpha minus beta times I. The general solution for this case would be y equals e raised to the power of alpha times x times the value of c sub 1 cosine beta times x plus c sub 2 sine beta times x. And in order to elaborate more on this topic and to find the applications of second order equations reducible to first order, I give you Miss Joycey.
Thank you, Mr. Omak, for explaining the concept of second order equations reducible to first order. And now, let's proceed to the application of second order equations reducible to first order, which is the application of case number 1. So, solve this equation: y double prime minus 5y prime plus 6y is equals to 0. So, let's talk about how we can solve this differential equation. So, first, let's write this quadratic function, which is ar squared plus br plus c is equals to 0, wherein our a is equals to 1, our b is equals to negative 5, and our c here is equals to positive 6. By replacing those values, we're going to have 1r squared minus 5r plus 6 is equals to 0. After that, now for this quadratic expression, we don't need to use a quadratic formula. We could simply factor it. We need to find the two numbers that multiply to the constant term but add to the middle coefficient. So for this equation, 1r squared minus 5r plus 6. Basically, our two factored numbers here is negative 2 and negative 3, because if we add negative 2 to plus negative 3, it would result to negative 5, which is our middle coefficient. But um, if we multiply it together, negative 2 times negative 3, it would result to positive 6. So, our factor here is r minus 2 times r minus 3 is equals to 0. So, our r sub 1 is equals to 2 and our r sub 2 is equals to 3 because we equate it to 0. Now that we have the values of r, we can write the general solution for this equation, which is y is equals to c sub 1 times a raised to the power of r sub 1 times x plus c sub 2 times a raised to the power of r sub 2 times x. By substituting the value of r sub 1, which is equals to 2, and r sub 2, which is equals to 3, we have y is equals to c sub 1 times a raised to the power of 2x plus c sub 2 times a raised to the power of 3x. So that is our general solution for this differential equation and also our answer. And I think that's all for the application of case number 1. I will give the floor to Miss Mariel Kailing, the next reporter.
Okay, now let's move on to application 2. I am Mariel P. Kailing, by the way, and I hope you will learn from me today. Okay, so let's have y double prime minus 6y prime plus 9 equals 0. We can observe here that RA is 1, B is negative 6, and C equals 9. Below the differential equation, we will write the formula AR squared plus BR plus C equals 0. So we will substitute the value of A, B, and C to this formula. So we will have 1r squared minus 6r plus 9 equals 0. In this quadratic equation, we don't need to use the quadratic formula anymore, as we could just use or conveniently use the factoring method to find the real root or roots of the equation. So when we factor 1r squared minus 6r plus 9 equals 0, the result will be r minus 3 times r minus 3 equals 0. Or we could simply write the quantity r minus 3 squared equals 0. So basically, r here is 3. So the result showed that we have only one real root, and that is 3. Now, in order to find the general solution of the differential equation, we will have the formula y equals c1e to the power of rx plus c2xe to the power of rx. We will plug in the value of r, which is 3, in this equation. So we will have y equals c1e to the power of 3x plus c2x e to the power of 3x. So that's how we can solve it when we will consider the second case. That's all, and thank you for listening. Now let me give the floor to Miss Coquilla to teach more about our topic.
Okay, thank you, Miss Marielle. So before I start, please bear with my voice because I'm not feeling well. Okay, so I'm having a hoarse voice, so please bear with me. So, okay, we have here the application for case number 3. So, we have solved the second derivative of y plus 8 times the first derivative of y plus 25 equals 0. So, here are the values of a, b, and c. So, we can also write this equation to a times r squared plus br plus c equals 0. So we can substitute the values here to this one. So we have a is 1, so we have 1 r squared plus 8r plus 25 equals 0. So we can factor this one. Okay, so we are going to use the quadratic formula. So we have r is equal to negative b positive negative times square root of b squared minus 4ac to the power of 2. So this is our formula to get the value of r. So substitute the values. We have negative 8 positive negative square root of b is 8 negative 8, so negative 8 squared minus 4 1 a is 1 and c is 25 to the over 2 times a, or 2 times 1. So we have negative 8 positive negative square root of this one is 64 minus 100, so we have negative 36 over 2 times 1 or 2. So it becomes r is equal to negative 8 positive negative 6 times complex number I to the over 2. So to simplify this one, we have negative 4 positive negative 3i. So from this one, we have two equations. So first is r sub 1 is equal to negative 4 plus 3i. And the second one is r sub 2 is equal to negative 4 minus 3i. So we can also write this one to r sub 1 is equal to alpha plus beta times I, and r sub 2 is equal to alpha minus beta times I. So we can conclude that our alpha is negative 4 is 1, and our beta is positive 3, this one. So since we have two equations or two values of r, we will use the case number 3, and this is the formula. Y is equal to e to the power of alpha times x times c sub 1 cosine times beta x plus c2 sine beta times x. So substitute the values, which is our alpha is negative 4 and our beta is positive 3. So our general solution is this one. Y is equal to e to the power of negative 4x times c sub 1 times cosine 3x plus c2 sine 3x. Okay, so that's it for the application of second order equations reducible to first order. Thank you for listening. And I hope you learned something from our topic.
Good day, everyone. I am Carl Christian Malesa, and for now, we will be discussing about the four applications of first order differential equations. And I was assigned to discuss about the first two applications of first order differential equations. So, without any further ado, let's get started. So the first application of the first order differential equation is the orthogonal trajectories. Orthogonal trajectories. Any curve which cuts every member of a given family of curves at right angles is called an orthogonal trajectory of the family. It is not necessary that the curve should intersect every member of the family. But if they intersect, the angle between their tangents at every point of intersection is 90 degrees. So orthogonal means perpendicular to each other. And if we say orthogonal trajectories, we have a point of intersection which is 90 degrees or right angle. So we have here the four steps. I have here four steps or four procedure to find the orthogonal trajectory. So the first step is let f of x, y, c is equals to 0 be the equation of the given family of curves, where c is an arbitrary parameter or an arbitrary constant. So the second step is differentiate the family of curves and eliminate c to form a differential equation. Third, substitute the negative reciprocal of dy over dx, or we have the negative dx over dy for dy over dx in the above differential equation of the orthogonal trajectories. Last step or last procedure is by solving this differential equation, we get the required orthogonal trajectories. So for us to have more knowledge or to gain deeper understanding with regards to orthogonal trajectory, I will be showing to you one example of how to find the orthogonal trajectory. So we have here, find the orthogonal trajectories of the family f of curves given by y squared is equals to cx cubed, where c is an arbitrary constant. So we have here the solution. The first step is identify the given family of curves, which is y squared is equals to cx cubed. Then the second step is differentiate the family of curves. Then we get, so we will differentiate y squared is equals to cx cubed. Then we get 2y dy dx equals 3cx squared. So we will divide both sides of the equation by 2y in order for us to get to only have dy over dx on the left side of the equation. So we have dy over dx is equals to 3cx squared over 2y. So since we are going to eliminate c here because we are looking for the orthogonal trajectory, so we will find the value of c. So how to find the value of c? So just simply solve the value of c in the equation y squared is equals to cx cubed by dividing both sides of the equation by x cubed in order for us to get the value of c. So by dividing y squared is equals to cx cubed, dividing both sides of the equation by x cubed, we get our value of c, which is equals to y squared over x cubed. So just simply substitute the given value of c, the calculated value of c in the equation, so we get dy over dx is equals to 3x squared over 2y times the value of c, which is equals to y squared over x cubed. So multiply, we get our value of dy over dx is equals to 3x squared y squared over 2yx cubed. Since the equation 3x squared y squared over 2yx cubed can be simplified to its lowest term by using the rule of exponent. So we get our value of dy over dx, which is equals to 3y over 2x. So now let's proceed to the third steps. If any curves intersects orthogonally at point xy, then we must have here dy over dx is equals to the negative reciprocal of the dy over dx, which is equals to negative dx over dy. So since we have already solved the value of dy over dx, which is equals to 3y over 2x, so just simplify the reciprocal of dy over dx. So we get dy over dx is equals to negative 2x over 3y, and that is the value of our the value of the negative reciprocal of the dy over dx. So we are here now in the last step. So we will now solve the above differential equation, which is dy over dx is equals to negative 2x over 3y. So next is we will separate the differentials and then multiply both sides of the equation by y. So we get y dy is equals to negative 2x over 3 times dx. So next is we will integrate the left-hand side of the equation with respect to x. With respect to y. And then the right side of the equation with respect to x. So we get the integral of y dy is equal to the integral of negative 2x over 3 dx. So next is we will evaluate the integral. So we get y squared over 2 plus c is equals to negative 1/3 x squared plus c. So since both constants of integration are arbitrary constants, we will replace them with the constant c. So we get y squared over 2 is equals to negative 1/3 x squared plus c. So next is we will multiply both sides of the equation by 2. Y squared over 2 is equals to negative 1/3 x squared plus c multiplied by 2. So we get y squared is equals to negative 2/3 x squared plus 2c. Since the expression 2c is a constant, it is possible to denote that the whole expression as a constant c. So we get y squared is equals to negative 2/3 x squared plus c. So just simply transpose the equation. We get c is equals to 2/3 x squared plus yc, plus c is equals to 2/3 x squared plus y squared is the orthogonal trajectory of the family of curves given by y squared is equals to cx cubed. So now, let us proceed to the second application of the first order differential equations, which is the rectilinear motion. When we say rectilinear motion problems involve the movement of an object along a straight line. So the position of the rectilinear motion is described by a function x of t, where t represents time. So I have here 4 steps for solving rectilinear motion problems involving position using derivatives. So we have here the step 1, which is if you are finding the displacement of the object over the interval or AB, evaluate x of b minus x of a, where x of t is the position function. if you need to find the distance traveled by the object, follow steps 2 through 4. So which is, our step 2 is to find the total distance traveled. First, find the velocity function, which is represented by v of t is equals to x prime of t, or the derivative of x of t, or the derivative of the position function. So the step 3, find where v of t is equals to 0. This is where the object changes direction. So the last step, or the step 4, divide the time interval into sub-intervals that will separate the two different directions of motion using the results from step 3. So find the total distance traveled by finding the absolute value of the displacement of the object in each sub-interval and adding the results. So for us to have representation, or to have more idea with regards to rectilinear motion, I will be presenting to you one example about rectilinear motion problems. So we have here the example. If the position of a particle is described by the position function, x of t is equals to t squared minus 5t plus 6, where t is greater than or equal to 0, is in seconds, and x of t is in inches. Find the displacement of the particle over the first 5 seconds. Then find the total distance traveled by the particle at the same time. So we have here the solution. The first step is we will find the displacement over the first 5 seconds. So we need to evaluate x of 5 minus x of 0 is equals to t squared minus 5t plus 6 minus t squared minus 5t plus 6. So since we are looking for the displacement over the first 5 seconds, we have x of 5. So now, just simply substitute the value of t in the given equation. So we get x of 5 minus x of 0 is equal to 5 squared minus 5 times 5 plus 6 minus 0 squared minus 5 times 0 plus 6. So simplify. So we get x of 5 minus x of 0 is equals to 25 minus 25 plus 6 minus 0 minus 0 plus 6. So we get 6 minus 6. So we have our value of x of 5 minus x of 0 is equals to 0. So the step 2 is we will find the total distance traveled. So first is find the velocity function, which is denoted by v of t is equals to x prime of t. So here we get v of t is equals to the derivative of the x of t. So we have here our derivative of x of t, t is equals to t squared minus 5t plus 6. So the derivative of this position function is equals to 2t minus 5. So that is why we get our velocity function here, which is equals to v of t is equals to 2t over 5. So now, the third step is we were going to find the v of t is equals to 0. This is where the object changes direction. The velocity is equals to 0 when v of t is equals to 0. So 2t minus 5 is equals to 0, and then transpose negative 5 to the right side of the equation. So we get 2t is equals to 5, and then divide both sides of the equation by 2 in order for us to find the value of t. So by dividing both sides of the equation by 2, we get our value of t is equals to 2.5. So that is our value of t. So for the last step is we are going to solve, since the particle changes direction after 2.5 seconds, we have two sub-intervals to use to determine the distance. So the first one is from 0 second to 2.5 seconds, and the second sub-interval is 2.5 seconds to 5 seconds. So now we will going to find the absolute value of the displacement over the interval. So we have We have here the absolute value of x of 2.5 minus x of 0 is equals to the absolute value of 2.5 squared minus 5 times 2.5 plus 6 minus 0 squared minus 5 times 0 plus 6. So then simply simplify the equation. So we get the absolute value of absolute value of x 2.5 minus x of 0 is equals to the absolute value of 6.25 minus 12.5 plus 6 minus 0 minus 0 plus 6. Then um, solve. So we get here the absolute value of absolute value of negative 0.25 minus 6. So subtract. So we get the absolute value of negative 6.25. So therefore, the absolute value of x of 2.5 minus x of 0 is equals to 6.25. And this is the displacement of the particle over the interval of 0 second to 2.5 seconds. So now we will be solving the second or the next subinterval, which is from 2.5 seconds to 5 seconds. So now we have here the absolute value of the displacement. The absolute value of x of 5 minus x of 2.5 is equals to the absolute value of 5 squared minus 5 times 5 plus 6 minus 2.5 squared minus 5 times 2.5 plus 6. So simplify the equation, we get the absolute value of quantity 25 minus 25 plus 6 minus the quantity of 6.25 minus 12.5 plus 60. So now simplify, we get the absolute value of 6 plus 0.25, then add, we get 6 absolute value of 6.25. So therefore, the absolute value of x of 5 minus x of 2.5 is equal to 6.25. So that is the displacement of the particle from 2.5 seconds to 5 seconds. So therefore, the particle traveled 6.25 inches between the interval of 2.5 seconds and 5 seconds. So our displacement is 0 inches. 0. Why? Because there's no changes in the two subintervals. Since our displacement value or the displacement of the particle from 0 second to 2.5 seconds and the displacement value of the particle from 2.5 seconds to 5 seconds is still the same, which is 6.25. So we have here our total distance traveled by the particle at the same time is 12.5 inches because we just add the displacement value from 0 second to 2.5 seconds and the displacement value from 2.5 seconds to 5 seconds, which are 6.25. So we will add 6.25 plus 6.25 is equals to 12.5 inches. So that is the total distance traveled by the particle. So I think that is my part about the applications of the first order differential equations, which are the orthogonal trajectories and the rectilinear motion. So I hope that you've learned my discussion about the orthogonal trajectories and the rectilinear motion. So thank you for listening.
So, hello everyone, I am Janilyn Paluga, and now let's talk about applying of first order differential equations on chemical solutions. So, chemical solutions are solutions in which some substance is varying because of certain physical or chemical actions that are usually analyzed in accordance with the following relation. So, we have here an equation: rate of change of substance in a volume is equal to the rate of entrance minus rate of exit. So we have here an example. The keg has a capacity of 1 gallon. Initially, the keg had 1.7854 liters of liquor with 10 milligrams of pure alcohol. So the valve of the keg is then opened and liquor is poured in the keg at rate of 1 liter per minute with a concentration of 15 milligrams per liter. The solution is being consumed or pumped out at a rate of 0.5 liters per minute. So we have here the questions. How long will the keg overflow and how much alcohol will be in the keg during overflow? So let's answer first letter A. How long will the keg overflow? So first, let's find the volume difference. So the volume difference will be obtained by subtracting the capacity of a keg minus the initial volume of the solution. So the capacity of a keg is 1 gallon, which is 3.7854 liters, minus the initial volume, which is 1.7854 liters. So the answer is 2 liters. Now let's find out the time fill, which is equal to the volume difference over the amount of liquid inflow per minute minus the amount of liquid pumped up per minute. Okay, so our volume difference is 2 liters over the amount of liquid inflow is 1 liter and minus the amount pumped out is 0.5 liters. All right. So the answer is 4 minutes. So next, letter B, how much alcohol will be in the keg during overflow? So we have here the equation, the rate of change of A, which is the amount of alcohol, with the respect to T, which is the time, is equal to the rate of inflow minus the rate of outflow. So this is from our original equation, which is the rate of change of substance in a volume is equal to the rate of entrance minus the rate of exit. So in here, we have to solve for the rate of inflow minus the rate of outflow. But first, we need to find what is the rate of inflow. So the rate of inflow is equal to amount of liquid flowing in the keg per minute, which is 1 liter per minute, times the amount of alcohol per liter, which is 15 milligrams per liter. So our rate of inflow is equal to 15 milligrams over 1 minute. Okay, so our rate of outflow. So we have here the amount of liquid flowing out of the keg per minute, which is 0.5 liter over 1 minute. We place 0.5 T there because we know that the inflow is 1 liter per minute. And this means that every minute there is 0.5 liter adding to the initial volume. So we have here A is A over 1.7854 plus 0.5 T. So that's why we get 0.5 A over 1.7854 plus 0.5 T. Then simplifying by 0.5, we have A over 3.5708 plus T. Let's log in this to our original equation. So we have the rate of A with respect to T is equal to our rate of inflow, which is 15 over 1, that's 15, minus the rate of outflow, which is A over 3.5708 plus T. So we have here our first order linear differential equation in the form of dA over dt plus PA is equal to Q, where P is equal to 1 over 3.5708 plus T and Q being 15. So we have here dA over dt plus A over 3.5708 plus T is equal to 15. We then solve for the integrating factor v, which is equal to e raised to the power of the integral of p dt. So it becomes integrating factor is equal to e to the power of the integral of dt over 3.5708 plus t, where where u is equal to 3.5708 plus t and du is equal to dt. So we can simplify our integral in the form of ln u. So we have here e to the power of ln 3 ln 3.5708 plus t. And the answer is 3.5708 plus t. Since we already solved for the v, now we will use the formula AV is equal to the integral of QV dt, where V is the integrating factor. So, logging in the values, we have A times 3.5708 plus T is equal to, our Q is 15, and to the integral of 3.5708 plus T dt, where U is 3.5708 plus T and du is equal to dt. So, simplify the equation. We have A 3.5708 plus T is equal to 15 times 3.5708 plus T raised to the power of 2 over 2 plus C. And then we have A 3.5708 plus T is equal to 7.5 times 3.5708 square plus C. So, take note that initially, the keg has 10 milligrams of alcohol. So, we have here, so our T is 0. So, plug in the 10, which is 10 times 3.5708 is equal to 7.5 times 3.5708 square plus C. So, from this equation, we will solve for C, and our answer is negative 59.92. And then we plug in the value of C. From the original equation, we have 10 times 3.5708 plus T is equal to 7.5 times 3.5708 square minus the C, which is 59.92. We have A is equal to 7.5 times 3.5708 plus T minus 59.92 over 3.5708 plus T. So remember that it takes 4 minutes for the keg to overflow. So with this, we can solve for A. So it takes our T is equal to 4. So A is equal to 7.5 times 3.5708 plus 4 minus 59.92 over 3.5708 plus 4. And then we have here our answer, 55.74 milligrams. So how much alcohol will be in the keg during overflow? So 55.74 milligrams of alcohol will be in the keg during overflow. So this is our answer. So that's it for chemical solutions.
Good day, everyone. I am Leralyn S. Lapastilla, and today I'm going to continue our topic. And now it is all about electric circuits. So, electric circuits can consist of a wide variety of complex components. This may be set up in series, or in parallel, or even as combinations of both. However, we'll be considering only series circuits with especially simple components: resistors, inductors, and capacitors, along with some form of voltage supply. So here is an illustration. L is a constant representing inductance and is measured in Henry. R is a constant representing resistance and is measured in ohms. C is a constant representing capacitance and is measured in farads. And lastly, E represents the electromotive force and is measured in volts. It is not necessarily a constant and may be a function of time. So, we shall consider here a circuit containing a resistance and an inductance in series with a source of electromotive force EMF. Resistance is a circuit parameter that opposes the current and causes a drop in potential given by Ohm's law, which is E sub R equals IR, where E, I, and R are measured in volts, amperes, and ohms respectively. So inductance is a circuit parameter that opposes a change in current and is analogous to inertia in mechanics. The drop in potential caused by a change in the current is given by E sub L, which is equals to L di over dt, where T is expressed in seconds and L, called the inductance, is measured in Henrys. For a circuit of the preceding type, a differential equation for determining the current I at the time t is L di over dt plus R I equals E, where E denotes the impressed EMF in volts, or EMF is electromotive force. Let's have here an example. If for equation 9, the current is initially 0, find the current at the end of t seconds. So, since 9 is a linear differential equation and its integrating factor is 1 over L multiplied by e to the power of RT over L. Thus, the integration, we obtain this equation number 10, which is e to the power of RT over L multiplied by I equals E over R multiplied by E to the power of RT over L plus C. Since I equals 0, when T equals 0, we find C equals negative E over R, and the equation number 10 may be written as I equals E over R minus E over R multiplied by E bar RT over L. So that is our equation number 11. So the solution. The term E over R multiplied by E to the power of negative RT over L is called the Differential formula. The Differential in the formula 11 because it becomes negligibly small after a sufficient lapse of time. The steady state term E over R agrees with the current expected by applying the Ohm's law alone. So I guess that ends our topic about the applications of first order differential equations. Thank you for listening and have a good day.
Good day to everyone. I am Nabal Kosain, and together with my co-presenters, Mr. Algin Baron and Mr. Joshua Abelinosa, we are going to talk about homogeneous and non-homogeneous differential equations. Me, the first presenter, together with Mr. Aljon Byron, we are going to talk about the homogeneous differential equations, while the third presenter, which is Mr. Joshua Abalinosa, he will be going to tackle about non-homogeneous differential equations. To begin with, I believe that in this particular topic, one should be able to have a general understanding or have a good foundation when it comes to differentiation and integration. It is because differentiation and integration plays a huge role in this topic, which is homogeneous and non-homogeneous differential equations, because in solving homogeneous and non-homogeneous differential equations, we are more on using differentiation integrations to find the solutions. Okay, so we will now begin. So a differential equation is an equation with a function and one or more of its derivatives. So we have here an example, an equation with the function y and its derivative dy over dx. So this is what a differential equation looks like. So I think that the determining factor to identify what a differential equation looks like is that we have this derivative, which is this one, dy over dx. So every time that you will going to see dy over dx, then automatically that equation is a differential equation. Okay, so here we look at a special method for solving homogeneous differential equations. A first order differential equation is homogeneous when it can be in this form: dy over dx equals the function of y over x. So again, a differential equation or a first order differential equation can be homogeneous if it can be in this form, this one, the function of y over x. So we can solve it using separation of variables. So we can solve this function using separation of variables, but first we create a new variable v equals y over x. Later on, I will be going to discuss deeper the separation of variables, which I believe is the method that we're going to use in solving homogeneous differential equations. So going back, before we can solve this equation, this differential equation or this function, first we create a new variable v equals y over x. V equals y over x, which can also be manipulated into y equals vx, and dy over dx. So we are going to use product rule on this one, so it will going to look like this. So dy over dx equals d times the quantity of vx over dx. We're going to use product rule, then it will equivalent to v dx over dx plus x dv over dx, and this one can be simplified into dy over dx equals v plus x dv over dx. Using y equals vx and dy over dx equals v plus x dv over dx, we can solve the differential equation. So before that, I will going to explain deeper what is the separation of variables, which I believe is the method that we are going to use in solving homogeneous differential equation. Okay, so I believe in this part this already been explained earlier. So this is what a differential equation looks like. And here is the question: when can I use it? When can we use separation of variables? So separation of variables can be used when all the y terms, including dy, can be moved to one side of the equation, and all the x terms, including dx, to the other side. So basically, we can apply or we can use the method of separation of variables if we can move to one side all the y terms and moving all the x term to the other side. So if we're able to, if in a given equation it can be the y terms and the x terms can be moved to either to the left side or to the other side, then separation of variables can be applied. Okay, so we have here three methods. So step 1, move all the y terms, including dy, to one side of the equation, and all the x terms, including dx, to the other side. Step 2, integrate one side with respect to y and the other side with respect to x. Don't forget plus c, the constant of integration. And lastly, the third step, we're going to simplify it. So we have here an example. So dy over dx equals k times y or ky. So in this problem, k is a constant. So let us all remember that k is a constant. So step 1, separate the variables by moving all the y terms to one side of the equation and all the x term to the other side. So here in this problem, dy over dx equals ky. We are going to move all the y terms to the left side and all the x terms to the right side. Okay, to do that, we are going to multiply both sides by x. So here, the first term, which is the dy over dx, by multiplying it by x, then the denominator dx can be cancelled and the remaining will be dy, which is this one. And here on the other side, we are going to multiply it by x or dx. Then we have, it will looks like this, k times y dx. Or the other method, aside from multiplying both sides by x, we can just simply cross multiply this equation. So by cross multiplication, so here there is an invisible one, ky has an invisible one, so this will looks like ky over 1. So cross multiplication, it will be 1 will be multiplied by dy, that's why here dy, and ky times dx, then this is it, ky dx. Then we were able to successfully move the x terms to the right side. Now we're going to move the y terms to the left side, and to do that, we are going to divide both sides by y. So from this, dy over dy equals ky dx by simply multiplying both sides by y. So here on the right side, y, there is over y here, so we are going to cancel y. That's why the only remaining left is k dx. On the other side, we're going to put here over y. That's why we have here dy over y. Okay, now we already achieved the step 1. We can now move to the second step. So the second step states that integrate both sides of the equation separately. So from this, we are going from this equation, dy over y equals k dx. We just simply put the integration sign on both terms. So here, put the integral sign in front. So we have here the integration sign, the integral sign, this one. And after that, we are going to integrate the left side, then followed by the right side. Or either way, you can also first integrate the right side if that is your choice. And we can also then followed by the integration of the left side. So here we're just going to first integrate the left side. So I believe that everyone has already know or have a good understanding or have a good foundation when it comes to integration. So by integrating dy over y, it will looks like it will equals to ln times the quantity of y. Then after integration, we should not forget the plus c. And now we're going to integrate the right side. So integration of k dx. So then it will equate to kx plus d. So why is it d? So we have here c is the constant integration. So here in the left side, c is the constant of integration, while d is the constant integration on the other side. So we're going to use d for the other side at this different constant. So this is in order for us not to get confused to the constants. Okay, now we're going to move to the step 3, which is we're going to simplify. So from here, this one, so after integrating, we arrive in this. So ln times the quantity of y plus c equals kx plus d. We're going to simplify that. So to be able to do that, we can roll the two constants into one. So a equals d minus c. So from here, so since c and d are constant, we are going to put them together by transposing. So this we're going to transpose to the other side. That's why from positive it will turn into negative. So d minus c, which is what happened here. And then this one will just substitute it to a to make it shorter. Then we have here e raised to the power of ln times the quantity of y is just equals to y. Okay, here, so let's take exponents on both sides. And then after that, e raised to the power of kx plus a is equals to e raised to the power of kx times e raised to the power of a. So here, and then e raised to the power of a is just a constant, so we replace it with c. So since e raised to the power is just constant, we're just going to replace it with c. Okay, then now we already have our simplified form. So we have here y equals c e raised to the power of kx. So this is just a general type of first order differential equation which turns up in all sorts of unexpected places in real world examples. And now we are back in this slide. So homogeneous differential equations. So at this moment, I will now be giving the floor to the next presenter, which is Mr. Aljon Byron. So I believe that he will be going to explain further about what is homogeneous differential equation, and he will going to give us some examples, and also he'll going to apply the method that I have discussed earlier, which is the separation of variables, which is very beneficial and also plays a huge role in solving homogeneous differential equations. Thank you.
Good day, everyone. So, for this time, we will be continuing the discussion on the topic homogeneous differential equation. And I am your second presenter, Aljun Byron. At this moment, we will be expanding your knowledge by giving some examples on how to solve the homogeneous differential equations. Also, we will be applying the steps and the procedures or the process on how to solve differential equation that was discussed by Mr. Kusain earlier. So if you're ready, let's go. All right. So earlier, Mr. Kusain discussed on the homogeneous differential equation, its definition. Also, he elaborated about the process on the separation of variables. So for this time, I'll be giving you some examples on how to solve the homogeneous differential equation. So here's our first example. So solve dy over dx equals x squared plus y squared over xy. But first, I have a question here. So can we get it in f times y over x style? So in this example, can we get this form, or can we solve it by this form? We will be discovering that later. So for now, how can we solve this one? So we will start with the given. So x squared plus y squared over xy. So the the next step is we have to separate the terms. So how can we separate this? So x squared over xy plus y squared over xy. So separating the numerator and just simply copying the denominator. So the third step. So we have to simplify. So if we will going to simplify our separated terms, we will come up with an answer x over y plus y over x. So the reciprocal of the first term, so we have to get the reciprocal of the first term. So y over x raised to the power of negative 1 plus y over x. So now, do we get the style f times y over x? Yes, we have a function of y over x. So let's go. So we will start with our answer earlier. So dy over dx equals y over x raised to the power of negative 1 plus y over x. So our next step is to uh, get the y is equals to vx and dy over dx equals v plus x dv times over dx. So we have here, we have come up with v plus x dv over dx. So this will become v raised to the power of negative 1 plus v. So subtract v from both sides. So we will get x dv over dx equals v raised to the power of negative 1. Now, we use the separation of variables. So how can we separate the variables? So using v dv is equals to 1 over x dx. So put the integral sign in front. So the integral of v dv is equals to integral 1 over x dx. So integrate this one. So we will get v squared over 2 equals ln x plus c. Then we make c equals ln k. So getting the c or making the c equals to ln k. So we have v squared over 2 is equals to ln x plus ln k, replacing the c with ln k. Then combine. If we combine this, we have an answer v squared over 2 is equals to ln k times x. So simplify this one, we get the answer v is equals to positive negative the square root of 2 ln times the quantity kx. So now we are done separating the variables. So we will be substituting back v equals y over x. So substitute this our answer earlier. So simplify by simplifying. So y, we have an answer y equals plus minus x times plus minus x the square root of 2 ln times the quantity of kx. And we have the solution. So this is the solution for our first example. All right. So now we will be giving you another example. So solve dy over dx equals y times x minus y over x squared. So can we get it f times y over x style? So we have the given. So then second step is to separate the terms. So separating this will come up to xy over x squared minus y squared over x squared. Then we simplify this one. This will become y over x minus y over x raised to the power of 2. And yes, we get f times y over x style. So let's go. So start with our answer earlier. Then we have this equals vx and dy over dx equals v plus x dv over dx. So v plus x dv over dx is equals to v minus v squared. So subtract v from both sides, we will get x dv over dx equals negative v squared. So now we will use separation of variables. So separating this equation, so we put integral sign in front. So the integral of negative 1 over v squared dv is equals to the integral of 1 over x dx. So if we integrate this one, we have an answer 1 over v is equals to ln x plus c. Then we make c is equals to ln k. So we come up with 1 over v equals ln x plus ln k. Then combine. So if you combine this, this will become 1 over b is equals to ln k times x. And then simplify. So v is equals to 1 over ln times kx. Did you get it? So after that, we will substitute back to v equals y over x. So we have our answer, and we have to simplify this one. So this will become y is equals to x over ln kx. And we have the solution. Alright, so did you understand the homogeneous differential equation? Or did you learn something on how to solve differential equation? I mean, homogeneous differential equation. So thank you.
Hello, good day, everyone. Happy New Year, and let me share my screen for a bit. Okay, so welcome, and for today's presentation, let me continue our topic on all about homogeneous and non-homogeneous differential equations. So we are the presenters, Mr. Nabel, Mr. Aljun, and yours truly, Mr. Joshua. Okay, to continue on non-homogeneous differential equation, uh, non-homogeneous differential equations are simply differential equations that do not, okay, as we have learned from the presentation of Mr. Nobel, they have conditions for homogeneous equations. So non-homogeneous differential equations just do not satisfy the conditions for homogeneous differential equation. This means that non-homogeneous differential equations are differential equations that have a function on the right hand side of their equation. So as you can see, uh, in this section, we learn how to solve second order linear differential equations with constant coefficient, that is equations in the form ay to the prime plus by prime plus cy equals to g of x, no? So where a, b, and c are constants and g is a continuous function. So the related homogeneous equation are ay double prime plus by prime plus cy is equals to 0. So in the homogeneous equation, we are going to equate, no, the function to 0. But in the non-homogeneous equation, it does not satisfy with the homogeneous in the sense that it has a continuous function on the right side of the equation. Alright? So, mura to siya, guys. Okay. The general theorem of the non-homogeneous differential equation can be written as function of x is equals to y sub p of x plus y of sub c of x, no? So, man siya imuhang general solution. Mo na pakita ng y sub p of x, no? And y sub c of x. So, where yp is a particular solution of equation 1 and yc is the general solution. So, ang yc is the general solution of the equation 2. Dari, so, mura to siya. Ang ito ang so there are two methods, but we're going to focus on the method of undetermined coefficient. So first, we're going to illustrate the method of undetermined coefficient of the equation ay double prime plus by prime plus cy is equal to g of x, where ang imong g of x kay polynomial na siya, it's a function. It is reasonable to guess that there is a particular solution of yp that is polynomial of the same degree as g, because if y is a polynomial, no, then a y prime plus b y prime double prime plus cy is also a polynomial. We therefore substitute, okay, substitute the values of y sub p of x, because it's a polynomial, the same degree as g, into the differential equation and determine the coefficients. Okay, so let's have some example. So just remember, guys, that as previously discussed by my team, the homogeneous equation, this one is not, it's the simplest form, no? So we're going to have it simplified, because if we're going to dig deeper on the non-homogeneous equation differential, it has so many sine, cosine, and all. So I guess we'll have to settle on the basic first, no? So I have here an example. So solve the equation y double prime plus y prime minus 2y is equals to x squared, no? So in the auxiliary equation, meaning in the parallel equation of the homogeneous, we equate it to 0, no? So it is r squared plus r, okay, minus 2. So the prime there is squared. If it's double prime, so it's squared. Okay, so just remember the factoring. So we have r minus 1. The factor of r squared plus r minus 2 is r minus 1 quantity times the quantity of r plus 2 is equals to 0. So we have the roots of the complementary equation, r equals to 1 and negative 2. So here, our yc here is c1 of e of x, no? Since your roots are 1, so your yc's equation is e of x, no? And plus your second root is negative 2, so you just replace the exponent by negative 2x, no? So since g of x is x squared, it's a polynomial of degree 2, we seek a particular solution of the form. So we have here, it's of the form, the formula na. of yp. So we have the yc. Remember, let's go back. The general equation is solution is yp of x plus yc of x. So we have already yp, sorry, yp, no, I sorry, yc. So we're now going to find the yp. So it is in the form of ax squared plus bx plus c, or the linear general equation of linear equation. Okay. So then yp is equals to 2 a sub x plus b, and yp squared is equals to 2a. Why? Okay. So since it is a degree of polynomial 2, no, x squared man. So as you can see there, it's x squared. So your yp, or the first derivative there, is 2ax plus b. Okay? 2ax plus b. So, imo siyang i-derive ang unang the first equation. And the second derivation is 2a. So, substituting it in the given differential equation, we have 2a. So, where's our given differential equation? Here, the ax squared plus bx plus c. Okay? Mm. Uh, it's on this general equation of y squared plus y minus 2y is equals to x squared. So, substituting na siya ay mong 2a. So, morgue na siya. Mangita ka sa roots. Kuan pangita sa roots. Solve ang yc. Ilisan ang exponent na to. And then, solve for the yp by deriving into the second derivation of the, if your g of x, or the function on the right side. And then, substitute it on the first equation. So, substitute na to. So, we have 2ax plus b plus, so your first, so the equation now is 2a, no, here, ano to dire, 2a plus 2ax plus b, no, minus 2 times ax squared plus bx plus c is equals to x squared. Okay, so we have now is equals to x squared, no? Okay, so we have now negative 2ax squared plus 2a times 2b times x plus 2a plus b minus 2c is equals to x squared. So polynomials are equal when their equations are equal. Thus, so we have negative 2a. So a is equals to negative 1 half. No? So we have here, muna siya, b is 2a minus 2b. So your b is negative 1 half. And your c there is 2a plus b minus 2c is equals to 0. C is equals to negative 3 over 4. So our particular solution is therefore 0 y of I of p is negative 1 half x squared minus 1 half x minus 3 over 4. And by theorem 3, the general solution is, atong general solution bitaw ang yc plus yp equals to, so copy paste mo ang yc, you have c to the power e x plus ce the power of negative 2x. So the yp is negative 1 half x squared minus 1 half x minus 3 over 4. So if g of x on the right side of equation 1 is in the form c of k to the x, where c and k are constants, then we take as a trial solution of function of the same form yp x equals to a e k of the k to the x, because the derivatives of k e k to the x are constant multiples of k to the x. So never mind the meaning of this. So we have the general equation and the solution sa ato ang example, no? So I guess guys, it's very easy to really master the non-homogeneous differential equation by going back to the homogeneous differential equation, since the non-homogeneous differential equation is just a uh, there is a function on the right side, wherein you're going to derive it into second derivation and then substitute it here, diba? Mao man ni no, g of x is x squared. So derive nimo na siya, may mo siya 2ax. So imong second derivation here is 2a. So asa man tong differential equation? Okay. Uh Sorry for the long pause, but I think that's all. So just follow the equation. I know that it's very, uh it's very confusing, but that's it for the non-homogeneous differential equation. Okay. Thank you everyone, and thank you for listening.